Morning, everybody. Welcome for this new seminar in the Instituto de Astrofísica Andalucía. And today we will have the talk by Dr. Mireia Nievas Rosillo from IIC in Canarias, Island. And the title is Towards the Standardization of the Analysis and Modeling of Multi-Wavelength Observations. So Mireia will be introduced by Daniel, who invited.
Good afternoon, everyone. It's a pleasure for me to introduce Mireia Nievas Rosillo. Let me talk about a bit of her background. So she earned her PhD in 2018 in the Complutense University of Madrid. And afterwards, she went to Germany for her first postdoctoral stay there. So she stayed there for 2 years in the DESI institution, where she was involved in the Veritas collaboration, that is one of these big Cherenkov telescope collaborations. And afterwards, in 2020, she moved to the Canary Island, to IIC, where since then she has been a postdoc researcher there in the IIC. So a bit of her expertise. So she is now involved in the MAGIC and LST collaboration, and also in the CTAO Science Consortium. And within this collaboration, she has like a quite important role in the extragalactic physics groups, where she has been, or she is one of the coordinators of these groups. And also she is an expert on the data analysis, multi-wavelength, not only gamma rays. And this is the topic of today's talk. So, Mireia, take it away.
So thank you very much for inviting me to give this seminar in your institute. It's a real pleasure to be here and collaborate with all of you. And well, the title of this talk sounds very technical and very maybe boring, which is data formats, how to standardize data. But you will see that there is a context for it, and it's really a need that we have right now with the advent of new instrumentation that are providing better and better data. No? So a little bit of the background of where we come from, etc., and why we now need this standardization of formats. Well, I come from the particle astroparticle physics environment, which is quite old already. It has more than 100 years of history, and it was born when people discovered that there was some radiation that was not coming from Earth, but it was coming from outer space. They did a series of experiments. They realized that this radiation had some effects in the atmosphere, and this is really the base of Cherenkov telescopes in particular. No? And one of the ways we have to detect, in particular, gamma rays of the highest energies. No? Now we know a little bit more about these particles. So now we see that there are several species, that they might have several origins depending on the energy. So we have from particles coming from the sun, then the typical galactic particles that are trapped in the magnetic field, and then the highest energies where particles have more rigid trajectories. We think that these particles might point to the original sources outside the galaxy. No? We not only have the protons, which are maybe the most abundant particle that we receive, no? But we also have heavier nuclei, we have electrons, positrons, antiparticles, but we also have a background of gamma rays and neutrinos. And these are coming from sources, right? Every time you have a diffuse population of some particle, this is coming from somewhere. No? So with this, you already will see that we have gamma ray sources, and we have detected many of those. No? So yeah. There are currently many instruments operating, trying to detect cosmic rays, neutrinos, and gamma rays, as you will see. So now centering on gamma rays, which is really the topic of this talk, together with the multi-wavelength. Gamma ray astronomy is not that old. It was born in the 60s, when it was already possible to send missions to the space, because, as you know, the atmosphere is completely opaque to these high energies. No? So this the first experiment, so in the 60s, they started to see that there was some radiation. It was correlated with the galactic, with some galactic emission. It is a similar development to, for instance, radio astronomy, no? In a way. But it was not only until the 90s when we sent the first big instrumentation, for instance, this Compton Gamma Ray Observatory with two major instruments, one profiting from the Compton effect, the other from pair production, when we started to really make successful sky maps covering the entire sky. No? Similar development on the ground happened with Whipple. It was originally created in the 60s, so it's super old, but it was not successful until the end of the 90s and the end of the 80s and beginning of the 90s, where we realized that putting here a camera composed by several pixels, we could take images of Cherenkov showers and therefore try to disentangle between charged particles and gamma rays. No? And this was the key for these instruments to really succeed. So what are we talking when we mention gamma rays? So we're talking about the photons that have the smallest wavelengths and therefore the highest energy. So if you take, for instance, a typical photon in the visible band, we are talking about the order of 1 electron volt. These gamma rays are 10 to the 9 to 10 to the 12 electron volts. So they are really, really energetic. No? They are everywhere. No? So you see, for instance, these beautiful all sky maps in different bands, and you see that obviously you have the Milky Way there that is emitting in almost all energies, but you also see the same thing in gamma rays. So there are a lot of sources of gamma rays in the galaxy. But you immediately also notice that there are several points that are completely outside the Milky Way, which are basically agents in the majority. There are some transient events, but the majority of them, they are agents. No? We also are now capable of creating sky maps, so we can really separate different components in some sources if they are extended enough. Of course, the PSF in gamma rays is really bad compared to, for instance, to radio or optical, so we cannot do as good as they do, but we can even resolve now some sources. For instance, the Graph Nebula, which is beautiful if you see the transition between different bands, you see different components there. This is basically non-thermal emission across the entire electromagnetic spectrum. You immediately see that we are at the limit of being able to already disentangle the different parts of this source in gamma rays as well. A way to judge the maturity of one energy band is to measure the number of sources that you detect. No? And you see immediately that in X-rays, for instance, that was born also in the 60s, the number of sources really exploded, and by the year 2000, there were already 10 to the 5 sources. So they really mature very fast, and now they can do a lot of things. No? We are a little bit behind that. So in the high energy band, so Fermi-LAT is really pushing this number of sources to already almost 10 to the 4 sources. So they are doing good. But now you see that this curve is really kind of plateauing. So this is telling you that the instrument is already pretty old, and only the slight increases in the exposure and the improved analysis methods are really pushing this, but of course very slowly. Similar thing happens with a very high energy regime. We are talking about maybe 2 orders of magnitude or 1 order of magnitude higher in energy. So around 100 GeVs or 1 TeV, the number of sources has really plateaued, and much before this in Fermi-LAT. And this is because the current generation ICTs, they are already quite old. They are more than 20 years old. No? So, I mean, we need something new, and this new thing will be CTO. This will hopefully push the number of sources to this threshold, psychological threshold of 1,000 sources. So hopefully with CTO, we will begin to start making population studies and really have proper statistics to do astrophysics. No? If you think, what are the methods to produce gamma rays? You immediately realize that if you have just emission as a black body, you will need incredible temperatures to produce gamma ray emission. And the luminosities of these sources will be totally crazy. No? So this is really not a promising mechanism to explain the gamma ray emission from these sources. In the majority of the cases, the emission across the entire electromagnetic spectrum of these gamma ray sources is dominated by two interactions. The first one is synchrotron emission, in which you have a particle that has been accelerated. I'm not going to enter into particle acceleration mechanisms because they are basically not clear. But imagine that you have a particle that has been accelerated in some way, and there is a magnetic field there. Then the particle will have a change in the trajectory because of the magnetic field, and this change in trajectory will cause radiation. No? And this radiation typically extends in, for instance, in AGNs, it will extend from the radio band to typically the optical or X-ray band. No? At higher energies, this is not sufficient typically, so you need something else. And this something else, what we think that is happening in most cases, is inverse Compton scattering. So now imagine that you have a low energy photon, typically from the cosmic microwave background, from some other source or some other component in the AGN structure, maybe from a star. This low energy photon might interact with an ultra relativistic electron that has been traveling here, and for instance is producing some synchrotron. And this electron will give some push to the photon, no? And it will upscatter it to the gamma ray band. We think that this is the major mechanism operating for AGNs in high energies in particular. There are other mechanisms that have been also recalled, such as hadronic interactions, in which you have, for instance, a proton-antiproton annihilation, an interaction with a proton and a photon, or even proton with a matter, with nuclei from the interstellar medium. And this can produce pions. This is necessary if you want to explain neutrinos. And you know that IceCube, for instance, which is a huge neutrino experiment in the South Pole, has claimed that they have hint of neutrino emission from several AGNs. So if you want to explain that, you need these kind of interactions. But we think now that these interactions, they are not the majority of what is going on these sources. So now that we know more or less what mechanisms do we have to produce gamma rays, let's talk a little bit about the sources of gamma rays in the universe. So first, let's start with the sources that are closer to us, galactic sources. And basically you have two things happening, no? Two processes. One related to pulsars and the things that are around the pulsars. So these are basically the residue of supernova explosions. You have a neutron star that is spinning very fast and has an incredible magnetic field. And here in the magnetic field, in some regions, you can accelerate particles very efficiently, no? And therefore produce gamma rays. Then related to pulsars, you have all other structures. For instance, the pulsar nebula that is being affected by the rotation of the pulsar, and basically you have a huge structure composed with a plasma that is also accelerating particles. And also about the supernova's explosion, sometimes you have these kind of shells. These are giant structures that are expanding. There is a plasma again. And this is a proper environment to accelerate particles and produce emission across the electromagnetic spectrum. Then the other way of producing this particle acceleration and gamma ray emission is by having a binary system. For instance, if you have a normal star and then some companion that is very compact, like a black hole, in some cases you can pass material from the companion to the compact object, and accretion disk is formed there, and in some cases you develop jets, which are regions where you can produce gamma rays. No? And finally, you have more explosive phenomena like nova, in which you have a giant star that is filling this Roche lobe, and some material is falling into the central object, which is into the compact object, which is typically a void dwarf, and at some point this becomes unstable and it explodes. No? Not going to talk about this, but these are giant structures that are now kind of a hot topic because they might point in some scenarios to a past activity from the Milky Way as some kind of AGN. But this is not very clear. In other galaxies, we also have sources like the ones I was mentioning before. So, for instance, in the Large Magellanic Cloud, we have detected, I think, a few pulsar nebula. We also have some explosions that are really bright. This is the case of GRBs, for instance, that have typically two phases. One that is the prompt emission that is really, really fast, and unless you are pointing there, you have basically zero chance of detecting it. And the other is an afterglow that sometimes is longer enough so that you can activate some DO program and point to that. And these ones we have already detected several in the DEP panel. And finally, the ones I'm gonna center more on are the active galactic nuclei. These are powered by accretion as well. And you have basically a supermassive black hole. And in some cases, you develop giant jets, which are really regions that are very efficient in accelerating particles and producing gamma ray emission. So let's talk about the ingredients, the basic ingredients, building blocks to construct an AGN. So you basically need a supermassive black hole and an accretion flow. If you don't have accretion, I mean, this whole thing won't happen. In some cases, you also have other structures. For instance, here you have some kind of dust structure that is surrounding the central object. And in some cases, this blocks the radiation that is produced here. It might reprocess it into the infrared. So this is emitting typically with temperatures of several thousands of kelvins, typically 10 to the 4, 10 to almost 10 to the 5 Kelvin. So this is in the ultraviolet band typically. And there is reprocessing into the infrared by the dusty torus. In some cases, this also blocks what is being emitted here. I think this side. Okay. This side doesn't matter. Okay, so in other cases, you might even have lines emitted in the optical spectrum. They come now. We know that they come from gas structures that they are moving in the structure of the AGN, and depending on how fast they move, the line will be broadened more or less. So, for instance, here you have a spectrum from a quasar 3C273, and you see several of these emission lines that are quite broad because this is a flat spectrum radio quasar. And finally, in some cases, but not all AGNs, this is really a minority, you develop giant jets. And these jets, they are basically plasmas of particles that have non-contiguous properties. So in the interface between those property regions with the same properties, the particles are really trapped. And we think that those are the regions that we know as knots, where really the acceleration is happening for the particles. Again, the major two mechanisms to produce the emission from these sources, the ones that have jets across the entire electromagnetic spectrum, are basically synchrotron emission and inverse compton. Sometimes in the optical, you see also thermal components, but in other wavelengths, they are just not there. And there is a question of whether these sources are also producing some hadronic emission and maybe neutrinos, Okay, depending on whether you observe the source in one direction or the other, because this really introduces a privileged axis, you will see different properties. And for instance, if you observe the source really with a large tilt with respect to the jet, you can really distinguish several parts of the jet very nicely, and the central object won't be magnified in intensity too much. So those sources, we know of them as radio galaxies, and for instance, resolving them with very high resolution instrumentation really give us a lot of information. We are not as lucky with blazars. In general, these sources are observed very close to the jet, and the emission that is produced in the jet is really magnified because of Doppler boosting. So in many cases, we don't even see the other components of the AGN. We don't see even the host galaxy in some cases. This, for many optical astronomers, they are very boring sources, particularly the VLAX, because you basically don't have anything but the synchrotron and inverse compton. There is nothing else. But for us, it's the sources that we can see more efficiently. So the spectrum, if you study it in the entire electromagnetic spectrum, so from radio to gamma rays, it typically has two components. One in the low energies, that is, we think that it's basically synchrotron. Here you see it. And then the high energy component, which we think is mainly inverse compton scattering. And what you see immediately when you put many of these sources, you see that there is kind of a gradient and some kind of behavior here, some kind of trend, in which the most luminous sources tend to emit at lower energies. And this, we think that is because these sources are emitting so much radiation that this effectively cools down the particles, And that's why they are not so energetic. While the most extreme sources, they don't cool that well the particles, and the electrons keep being accelerated more and more. No? AGNs in general are super variable. So here you see an example of a quasar that is changing really fast the emission in the Fermi-LAT band in gamma rays. And as you can see, there are several flares when you study the light curve. So the emission as a function of time, you see that it increases and decreases the emission continuously. No? These kind of campaigns are really important. They provide us a lot of information about what is going on in the source. No? But of course, this will generate also very challenging data sets to be analyzed, no? As we will see. Another thing that we can try to do is to try to get information about how the spectra of the source change, no? And this is really pointing to changes, for instance, in the electron population, in the underlying electron population. Maybe there is some fresh injection of particles and they diffuse, they cool down, etc. No? This is what we want to do. We want to study the physics behind this gamma ray emission, which is the kind of the messenger, no, in this case. So how do you approach this problem? You typically try to introduce models that start with the basic things, which are electron populations with some spectra, energy spectra, and then you try to see how these electrons cool down, etc., no? And how this translated into changes in the multi-wavelength behavior of the AGN, no? And the basic ingredient to do that is typically to have measurements of how bright the source is in different wavelength bands, no? So this is what is done here. For instance, they were taking some flux points at different energies, and they were trying to try some modeling and some fitting of the model with some fitting of the data with these models. No, again here you have another work with some other code radiative code. And they see that there is some constraints on the parameters, for instance, the density of electrons, the spectral indices, etc. No? But of course, this is not fully correct, because what you are doing here is to take flux points, assuming some Gaussian statistics. And this is not correct in some cases, particularly if you, in the regimes of low counts, these Gaussian statistics really fall apart. So fitting flux points in general is not ideal. You have many problems that are there. So for instance, the assumption of Gaussian statistics everywhere is not correct. There is no easy way of including non-detections. For instance, if you observe a source and if you don't detect it in gamma rays, that's telling you something, no? And if you cannot include that information, I mean, you are wasting your observation completely, no? And using flux points is really not ideal for this, because you have to invent somehow the likelihood profile if you want to fit that data, no? In other wavelengths, for instance, in X-rays, we use tools that are not designed to produce these flux points, but we still use them in an improper way. We are not very proud of it. We hide it in our publications, etc. No? But still we do it. In the optical band, for instance, you have flux densities. You don't have a measurement of this SED, this energy flux. And in order to convert it to this quantity, you have to assume a spectrum of the source. And if you only have one measurement in one band, let's say in the red band, I mean, what spectrum do you assume? It's not trivial, no? You ignore completely flux point correlation, and in some band this is really not okay. For instance, in the X-ray band, all points that you are generating here, they depend on the assumption of the spectrum, and that's the case also for Fermi. No? And finally, you are kind of freezing the model when you reconstruct it in different bands. You are kind of freezing the assumptions, and you cannot update them as needed to test some models. No, for instance, here, if you assume some spectra with some index in some band, then if you want to change it because you want to test other models, you will have this under the hood, no, without being able to change it. So this is not ideal, but is there any way to do it better? Yes. We here introduced another technique that is kind of the inverse of this one. No? So what I was mentioning until now is doing some kind of unfolding. It's kind of having an image like this one that has been degraded because of the instrument, and you are trying to recover the original information that is telling you about the physics, no? So in principle, the models really predict this, no? This is your model prediction, no? But you have this one. So the thing that is traditionally done is to try this sharpening of your image, of your data, in order to invert what is being done by the instrument, no? This is very cheap because you do it once computationally and then forget about it. But it the same as sharpening an image, it introduces artifacts, introduces some problems. Normally, it doesn't converge to the proper solution. It converges to some solution, but maybe it's not the correct one. So normally, you basically introduce some techniques like that are called regularization, etc., in order to stabilize this process, no? This inversion of this, let's say, matrix, no? And this makes your data model dependent. The flux points that you reconstruct are correlated, etc. No? So this is not trivial to do. The other way to approach this problem is to do the opposite, which is called folding. So you start with a model that is predicting you this beautiful image or whatever, and then you convolve it with your instrument model, and you get something that you can directly compare with your measurements. In this case, the number of counts in some instrument, no? So this is what we want to do. But until now, it was complicated because constructing these instrument models is not that easy. And in the end, it's very CPU intensive because in each iteration, every time that you change one parameter here in your original model, it will you will have to convolve it again with the instrument in order to update your expected measurement. No? So this is not cheap. It comes with a cost. But there are several tools already that are being developed in the field in order to do this in a multi-wavelength context, no? Taking several instruments across the electromagnetic spectrum. There are basically two different ways of approaching this problem. One is the one proposed by 3ML. This is a tool that what it does is to take every single analysis code developed for each instrument, and it exposes the likelihood functionality of that code. No? For instance, you take X-ray data, which is analyzed with the X-ray tools plus XPEC, and then you export the likelihood produced by XPEC. Of course, this is very nice because it uses the native tools developed by experts for each of the instruments. So you are more confident about the correctness of this solution. But as a con, it is obvious that you have to set up an environment where all the software is installed. All these softwares are installed, and you know that this, in practice, is not that nice, and sometimes it is even impossible. The other approach to the problem is to, instead of exposing the likelihood functionality of each of the codes, is to convert all the data and all the instrument models into some common format, and then have a code that, taking that, can build the likelihoods for each of the instruments. No, and this is what Gammapy does. No, so it puts everything into some common format, and then you have a code that can be applied to every kind of instrument. No, of course, the major problem of that is that you have to convert the data, and in many cases you have to start from scratch and develop this conversion tool by hand. No? But it has a very nice pro, which is data portability. So once you have converted the instrument model and the data, you can just pack it, send it to a friend, and that friend with some code that has some emission model or emission code developed can really test the data properly. So this is really what we want to do. So Gammapy operates in using some concept, which is the concept of dataset. No, here I'm gonna talk only about binned datasets. So you basically work with histograms that can be either in 3D, so you have the spatial components and the energy axis as well. So it's kind of a 3D histogram. Or 1D datasets in which you basically count number of events as a function of energy in some regions, no? Specific regions. I'm gonna forget about these ones because these ones are the ones that we are trying to avoid. No, these are the flux points that are ugly and horrible. Okay, so starting, I'm not gonna enter too much in details, but starting from Fermi-LAT. Fermi-LAT is an instrument that has a very poor angular resolution, particularly at low energies. So you are forced to work with 3D data sets because you will get a lot of contamination from other sources, from diffuse components, etc. No? So you will have to produce a 3D data set for this one. You cannot just count events in the region of interest and forget about it. This is how more or less a data set in 3D looks like. Of course, you cannot really plot it in 3D here. So what I'm doing here is to project it in the relevant axis, either spatial axis or energy axis. And basically what you need is a counts cube. So this histogram of number of counts as a function of position and energy. Your model map convolved with the instrument response functions. This, every time you change the model, will change. Of course, this is the prediction that you are going to compare with the observed data, number of counts. You need the PSF, and ideally you will have the PSF as a function of position in the detector. Then you need the energy resolution or energy dispersion matrix. So the way the reconstructed energy of each of the events relates with the true energy. This is telling you the energy resolution at each of the energies. And then a measurement of the how effective you are detecting photons. No? And this we typically measure as an effective area of the detector. No? So in principle, you have the collection area, which is the total thing. And then, of course, at some energies, you might not be that sensitive. So the effective area is scaled down. No? Fortunately, all these components are given by the Fermi tools already. So there is not that much that you have to do to construct this thing. Basically, you start with some event list that is produced by the Fermi tools, the Fermi analysis tools. And also the Fermi tools gives you the PSF information, the effective areas, the energy dispersion matrix, everything. No? Going down in energy, now we can go to something simpler, or maybe we are forced to go to something simpler in X-ray, because generating the background models in X-ray is not that trivial. I mean, for instance, if you take Chandra data, what they typically do is either go to 2D analysis or generate images that are integrated over energies, or study the spectrum of some source. But normally they don't do the two things at the same time because it's really complicated in X-rays. No? So here what we are working with are histograms of number of counts as a function of energy. And we can forget about the PSF. We don't need that. And the spatial distribution of, for instance, the effective area, we don't need that as well. So you basically start with your image in which you set up some regions to measure the source flux and the background flux, and you integrate the events in those regions. So you produce these histograms for your source, for the background. You have to be careful here in order to have at least some events in the background, because otherwise even the Poissonian statistics cannot be applied. But otherwise, this is very simple to produce. And the exposure and the energy dispersion, they are given by the collaboration, the Swift experts, so you don't have to do that much about it. U-Bot is very similar. So U-Bot in principle is an optical ultraviolet instrument that has a CCD. So it should be similar to optical telescopes on the ground, no? But actually the way that CCD is operated is more similar in many ways to how X-ray telescopes are operated. And what you measure are single events. So the pipeline to analyze that data is very similar to the one that is used for X-ray data, no? But otherwise, it's very similar. It also has the same kind of input to build the data set. It's also a 1D data set, but in this case, each of the data sets consists of data from only one filter. So there is only one channel. There is no migration matrix per se, no? But otherwise, it's super similar. And now let's go to something a bit more manual or a bit more convoluted, which is to deal with optical data from the ground. No? Here there are a lot of complications because you have the atmosphere. This will change your detector sensitivity at different wavelengths, so it will introduce a non-gray effect in your effective areas. But let's, for now, forget about this and take the response of this instrument from the filter profiles, no, the filter transmission profiles. So now we have for the effective areas for this exposure, we will have the filter profile here, the filter transmission, but we need to know where to put it, no, where to normalize it. And to do that, there are several tricks. Either you take some calibration star in some region close to your source, or you just take your image, and if you are lucky enough, you will have some stars that you can use as calibrators. No, so this is typically done, for instance, for differential photometry. No, so let's do that. Let's take some stars here that we can measure the flux in number of counts, and if we are lucky enough, these are good stars, they are not variable. We can check in some catalogs that this is the case. Maybe if we are lucky enough, there will be a good measurement of the flux emitted by this source in that band, no? By these stars in that band, no? So we are ready to really set this normalization on each of these bands, no? Okay, and now it's time, once you have set your effective areas, it's time to do the other way around. So now we are interested in our source of interest, in our quasar, for instance. So we set the regions for to measure the counts from the source and to estimate also the background. This will have Poisson statistics if you compare them to photoelectrons. And with this, you're ready to build the data set in Gammapy, which is it's actually pretty easy. But not only photometry you can also play with the spectroscopy. So here I'm using a tool that was designed for gamma ray astronomy, but I'm using it to analyze some spectral data in optical. So this is pretty cool because we followed a quasar that was some TO observations in ST, and I took some spectral data with SPRAT. This is a low resolution but very high throughput instrument in Liverpool, in La Palma. Sorry. And what is nice about this instrument is that magnitude 15, let's say, in optical, you can take a spectrum in just a few minutes. So this is really great, no? The resolution is not the best, but you don't care about this because you have basically non-thermal emissions, so you are not expecting too many features, no? So here, what you can do, for instance, is to take a spectrum of a star very close to your source in order to reconstruct the exposure. You know the spectrum of the star, so you can really know if you observe some counts at different wavelengths, you know how sensitive your instrument is, no? So you can build this cube, which is one of the inputs that you need to build the data set. And the other inputs is to measure the background, the spectra in raw counts of the background and your source of interest here, which will have Poisson statistics, no? So with this, and then the energy dispersion, which you can get from the resolution of the spectrograph. Let's say you have R300, then you know how wide this band is, this confusion band is. So with this data, you can build a data set, no? And you can do very cool things. For instance, you can combine this spectra for different reasons, for different nights. Here, for instance, I took for this quasar with the 2 reasons that Liverpool Sprat offers for the 2 nights. So I have 4 data sets. I put a model that is very simple. It's a power law spectrum model. And I allowed it to change from one night to the next in order to study what is changing in the electrons. And then on top of that, I allowed for some optical emission lines to be there, no? In order to try to constrain them. So these lines, of course, they will vary very much slower. So I basically freeze them and yeah, I constrain them with the 4 data sets at the same time. You can even do something even cooler, which is combine spectroscopy with photometry and fit everything together, no? So this is what we did actually. So here you have a constraint on the spectrum by the 2 grisms for the 2 nights and the 5 photometric filters at the same time, no? And as you can see, the error bars here are tiny. This is amazing that you can distinguish such small changes in the electron properties, no? Underline this source emission. This is amazing. And imagine the kind of physics that you can do if you can constrain the synchrotron emission with this optical spectroscopy, and at the same time try to constrain the inverse quantum emission with the rest of the multi-wavelength spectrum, no? So just to show you some use cases of this, or things that we have already done, We have studied here a quasar over 10 orders of magnitude, doing this forward folding for these multiple instruments from optical using Liverpool, also including some ultraviolet data from Swift, X-ray data from Swift XRT and NuSTAR, and then Fermi-LAT data. And here what we were doing in order to validate the method was to compare it with the classical flux point fitting. No? And you immediately realize that there are some differences here. No? For instance, there are regions like in starting from 70 kV in NuSTAR, where you don't have any sensitivity to the incident photons because the instrument is completely blind, but you still get some constraint here because for NuSTAR, you, apart from the source of interest, you have some instrumental background that is affecting the entire detector, no? And you can constrain that instrumental background with the regions where the instrument is blind. Something similar can happen here, for instance, with Fermi, the regions where you don't expect anymore to have emission from your source because of EBL attenuation, for instance, you still can constrain the other sources and the background because the detector is still seeing events, no? And this is something that you cannot do with the flux point fitting. No? So you have much more freedom to include sources, other sources that can be varying, other components such as the backgrounds, the instrumental backgrounds, etc. You can play with the absorbers and have the correct contribution of this. No, so imagine that you want to now include an absorber that is in the host galaxy. No, this with the flux point fitting will be not ideal, but with this technique you can in principle implement it very easily. And even for this case that is very simple, you don't have upper limits, you don't have anything, you have a very clean signal across all the bands, you still see some differences. So this is really telling you that you need to be careful when you treat your statistics, your statistical analysis, no? And if you don't do it properly, you might end up with some bias in your results, and therefore your interpretation, no, of this. By the way, these datasets, we have uploaded them together with all this code to analyze it, to construct the datasets, to everything to a GitHub repository, and also it's described in this paper, so you can just go there and play with the data directly, or see how we did this kind of analysis. Another use case that is obvious is the study of this extragalactic background light. So this extragalactic background light is just a soup of photons in the optical and the infrared band. So this is basically light reprocessed from the optical component. But this mostly composed by star emission, aging activity, etc., across the history of the universe. So it includes very valuable information about the star formation history, the evolution of the universe, even cosmology, because the way the universe expands will affect to how the EBL changes with RefSit. But so we want to really measure it and constrain it. And it's actually pretty bright. So if you take the intensity, it's not that much weaker than, for instance, the CMB. However, as opposed to the CMB band, here we have incredible foregrounds, no? that make it impossible to directly measure the EBL. No? So for instance, inside the atmosphere, you have the air glow, the sky glow, extinction, you have many effects that really hides this measurement. Even if you go outside, you still have the zodiacal light in the solar system. You have the galactic emission, even if you manage somehow to leave the solar system with the New Horizons, for instance. And finally, you have individual sources that introduce kind of anisotropies here that hide you from this underlying soup of photons, no, on diffuse radiation. So there are several ways to approach these measurements. As I said, direct measurements are very complicated. They are plagued with systematic uncertainties. So we need to look for something else. Alternatives include counting galaxies. So if you can get from very deep catalogs of galaxies and somehow reconstruct the spectrum of these galaxies, you can integrate the total lights that these galaxies are producing, which will be the bulk of the EBL. But still, it will be always a lower limit. So, no? There are other methods that people have thought that are kind of tricks using some effects. And they're actually pretty smart. For instance, looking at some dark cloud, if you are lucky, that dark cloud will be quite far away, so there will be not that much interstellar medium behind it. And if you compare it, measurements, photometrical measurements in that direction of the cloud with respect to some other direction very close to it, you can effectively constrain what is behind the cloud, no? And if you are lucky enough, this will more or less approach what the EBL contains, no? But of course, these are tricks. They don't work in every wavelength, so they have a lot of limitations. And the final way to access this is through the interaction of this EBL with the gamma rays, no? If you have a very distant source like a quasar or a GRB that is emitting gamma rays, these gamma rays that are very high energy interact with the low energy photons from the EBL, and they produce pairs of particle-antiparticle. So in principle, this radiation gets attenuated. And this attenuation, if you have some spectrum that looks like this, it's let's say a log parabola, this attenuation will be stronger the higher you go in energy and the farther away you go in ref signal. So in principle, if you can somehow reconstruct this intrinsic emission and you have the absorbed emission, you can compute this, no? The way we usually approach this problem is slightly different. So we typically take one of these predictions of the EBL spectrum, taken from instance from catalogs of galaxies, and we basically change the overall intensity of the EBL. This overall normalization, you can convert it into an overall normalization in the opacity that you expect for gamma rays, that is as a function of refsit and energy of the gamma ray photon, no? So this is basically the game, and we basically do some kind of scans in which we set this normalization to some value. We try to find the model that best describes the observed data and change in each iteration this normalization, no? And we see that there is some value in which our expected emission really reproduces the best our observed data, no? And this is what we think that is the EBL, no? You can play with the different EBL models with different assumed spectra, so you get different constraints to this overall intensity, no? And this will be very, very nice because it allows you to do something that is very cool, such as, for instance, constraining the star formation history using gamma ray data, no? This is just entering into real astrophysics now, no? So for instance, in this work by the Fermi collaboration, they were using Fermi-LAT data in the gamma ray band to constrain the star formation history and compare it with measurements that are completely independent. So this is another way to approach these models. Even more, you can play with the cosmological parameters, because those cosmological parameters will affect how the EBL changes with refsit. So if you measure the EBL at different refsits, you have an independent measurement of these parameters, no? The Hubble constant, the matter content of the universe, etc. And there are several works that having done this, and this is completely independent than other measurements, including this distant ladder or the CMB measurements, no? So just to conclude, I hope I have conveyed you that first, the gamma ray field is starting to get mature. We have already quite a number of sources, so we can start to play a little bit with this data. But of course, having better and better data, particularly in a multi-wavelength context, comes with a cost. If you want to explode it as much as possible, you need to have the proper tools, no, to manage it, because otherwise you will always fight with biases and problems, no? So Gammapy really offers one of these tools to fix one specific problem, which is the use of these flux points that is completely incorrect to do these interpretations. And here I hope I have conveyed you that the message that even though it is a tool that was designed originally for gamma ray astronomy, you can use it for all kinds of instruments from many bands, from different types of data, for instance, having 3D histograms, having 1D datasets, etc. No? It has a better statistics, let's say, because maybe even Poissonian in some cases is not enough, but at least you are not assuming Gaussian statistics everywhere and live with that. Allows to use non-detections, has a proper management of the backgrounds of other contaminant sources in your data. You can fit together, for instance, optical photometry and spectroscopy and have a common interpretation on the results. And yeah, it avoids many issues from that you have with the flux points, for instance, the correlation of them. No? So where to go from here? There are several possibilities. You can try to integrate in the game better physical models in order to have constraints on the particle populations. This is what we are trying to do now. Maybe we need fancier fitting techniques because now the models are very degenerate, but let's see how this goes. We can try to extend it to other parts of the spectrum. Maybe you can go even lower in energy to the radio band, maybe. You can try to extend it to other messengers. I know there are people, I think, trying to see if they can apply it to neutrinos with IceCube. Maybe you can apply it to polarimetry. You might need to change a little bit the dataset format, but it's worth to experiment with that. And finally, it offers some possibilities to really do multi-wavelength 3D analysis. So you study how the energy distribution of the events changes with some sources. To study, for instance, how these particles diffuse, how they radiate, how they cool down, etc. So it really offers a lot of possibilities, and it's a matter of getting there and starting to develop the tool for it. And with this, I conclude. So thank you very much for hosting me for during this time, for offering me the possibility to give this talk, even if it was super technical. But yeah, thank you very much.
Thank you, Mireia. So the talk is open for questions. Daniel, do you want to
time for questions? We have microphone or something.
No.
Okay. Well, first of all, thank you very much for the Mireia. It was very nice. And I wanted to ask you about the last part of the EVL constraints.
Mm-hmm.
I didn't exactly get how do you use the tool in order to constrain the EVL. I mean, you have the data set and you perform a full likelihood.
Yeah, so I mean, let's start with how people did this in the past, and there are still people doing that in the field. And what they get, then they have some claims of having detected some source for which the attenuation is very low, and then maybe you have action like particles, etc. So all these things usually come from one simple fact. So imagine that instead of fitting some underlying counts, histograms or something like that, you have some flux measurements at different energies. So you have some flux points here, and you fit them. I mean, this is in principle correct, no? But if you don't have a detection here, if you have an upper limit here, how do you include that? So imagine that now you have a spectrum for which you have some fluctuation at the energies where you are almost at the limit of sensitivity. If you have a positive fluctuation, you will reconstruct a point, so you will bias your result towards a larger value. If you are not that lucky and you have a negative fluctuation, or if you don't have a fluctuation at all, you will put an upper limit and you will just completely ignore that energy. So, I mean, this introduces problems. So what we are trying to do here is something totally different. So what we start with is some model. For instance, here, imagine that we take a log parabola emission model that has 2 parameters, 3 parameters, and we can predict the intrinsic for the intrinsic emission. So we assume that that's the emission of the source in that band, right? And then we convolve it with the instrument response functions of Fermi-LAT first, to produce the thing that the prediction, the number of predicted counts for Fermi, and we do the same thing for some Cherenkov telescope, for instance, at higher energies, to predict the number of counts that we should see. And this number of counts, we compare it with the observed data for the 2 bands. This was not possible before. So when we did not have this data, for instance, in the MAGIC paper, we couldn't produce this kind of forward folding for Fermi-LAT. So what we did was something more basic, which was to use the overall shape that this spectrum had at low energies, and then really do the forward folding only in very high energies. But this is limiting. Now it becomes possible to do this. This has never been done before, and it's much more powerful. But because even if you don't have a detection here in very high energies, you will still constrain the data with those very high energies.
Ivan?
Thank you very much, and also for the rest. It was very interesting. And I have a very similar question. If you can show this slide where you are showing the spectral fit together with the photometric measurements, and actually about the fit, because you were talking here actually,
or here.
The next one, yeah, we were talking here about extracting physical parameters from the system by the different fits, because I understand that these are two different epochs of data or something like that.
It's one day after, more or less.
Yeah,
they are
different
something, but it is the night after.
You were talking about extracting differences in the physical parameters of the source from this data. That involves that actually you apply a particular model.
I cheated a little bit. So here I'm not using physical models that model the electron population. I'm just assuming some power law, emission, whatever. But in principle, it will be possible. But in principle, it should be possible to substitute it completely by some synchrotron emission model that has the properties of the electrons, and then fit your data here. So it should be simple in a way.
But even in that case, what I see is that even in the more complicated case that you use a model, actually your interpretation of this complex data set will be also model dependent. It would depend on the model that you use.
Yeah, sure.
And they are all of them using assumptions and so on. I agree. I mean, the tool is fantastic in the sense that you can combine the data in a way that was impossible to do before. But we still have the problem that the models have limitations or too much parameters or strong assumptions. No?
Sure, but I mean, you will have always these problems, and there are ways to for instance, in these too many parameters, too much degeneracy. There are works that go in that direction. For instance, using this nested sampling that is basically covering the entire posterior distribution in some fancy way. Using Bayesian analysis. I mean, these techniques already try to go in that direction. So even if you have one of the test benches that they start with some very, very degenerate solution in which you basically have the same likelihood in several different positions, no, in the space of parameters. So it's completely degenerate problem with no unique solution, and even that's one of the test benches that they typically use for that. And yeah, you will always have this, and maybe this likelihood fitting thing is not ideal for that. Maybe you need a Bayesian interpretation. I mean, there's no unique solution. There is, under some priors, you have different solutions. But really, the technique is not limited to do just let's say a fit with one of these. A simple fit, you can introduce here the Bayesian framework very easily. In fact, there are people who are introducing that in Gammapy already, who are playing with these Bayesian frameworks.
It's a bit similar, and I was curious about you said the forward folding is very time consuming compared to the unfolding. Wait, don't go back.
Okay.
In the next slide to this one, I think, yeah, you showed this 10 order of magnitude forward folding. How long did that take to compute, for instance?
This one, I think 20 minutes, 10 minutes, not that much. And it has many instruments. It's actually pretty fast. No, but in every single iteration, instead of just fitting some flux points that you reconstruct them and then you freeze everything. And then it's super easy because your model prediction your models they will predict is some flux. So if you have the flux point, it's super easy to see if that is well reproduced by the model, no? So that's super cheap. Once you have done the convolution, it's super cheap to test different models. With the forward folding, you need to convolve in every single iteration the model with your instrument, no? And do that for multiple instruments. So, I mean, that takes more time. That's the whole point. But we have seen already cases in which this converts better to the proper solution. And we think that this is because, I mean, fitting in the counts space, I mean, it's more natural to the data that fitting in something that is assuming many things and even not correct. And here you see, for instance, that even if you have a pretty nice data set with a, very nice constraints, errors that are not too high, except for maybe the Fermi band, etc. There is no upper limits, there is nothing. Even there, the results are slightly different. Not very different, but slightly different.
Just out of curiosity, if I'm involved with astronomy as well, so I wanted to know if you have an idea about how to include radio data in that kind of.
I have no idea. I need to talk to you and check some radio data because I have never played with any radio data set.
Let's talk about.
But I guess what you do in radio is using this clean method, which is in a way some kind of iterative unfolding, no? In some way.
That's more complicated.
Okay. Okay.
And there is also a variety of different kinds of radio data, like imaging, single vision, something. Let's talk.
Also for polarimetry, maybe we need to modify a little bit the kind of data set that we have because the reconstruction is a little bit different, but I don't see any fundamental problem why this wouldn't work. And it would be a way to test models that predict different, there are already models in the market that produce different changes. For instance, if you model a light curve, so they predict changes in the polarimetry. Would be a way to test that.
More questions online? Is there any questions online? Nope. No, so let's thank Mireia again.